Okay, so ready?
Yep.
Okay, all right, I will start. Good morning, afternoon, evening. Hola, hello, bonjour. Hola, ni hao, konnichiwa. 안녕하세요, and hello all. And welcome and thank you for joining us, the 39th seminar and SynBERC Day. I am joining SynBYSS from Korea at midnight after my 16th talk in a conference today, actually yesterday. I discussed plastic upcycling and climate crisis today. Actually, yesterday, I keep saying today, because now the midnight, after midnight, as a keynote speaker here, I have 5 more weeks of my 10-week world seminar tour, and I will join you from Cancun, Mexico next week after giving my talk again over there in one of the ECI conference. Actually, Jay Keasling, today's the pioneer speaker, also joining in person, so I'm super excited right now. And then, yeah, that's also my 17th talk of this tour. Okay, it's my absolutely tremendous honor to introduce very briefly our pioneer speaker, Professor Jay Keasling. Of course, he does not need any introduction because we all know him. Briefly, he is, of course, a professor at UC Berkeley and also senior faculty scientist at Lawrence Berkeley National Lab and chief executive officer at Joint Bioenergy Institute, so-called JBEI. Most importantly, he was the director of SynBERC, the first synthetic biology center in the world, leading the synthetic biology field and encouraging other countries to start similar centers. So after that, UK start the synthetic biology center, etc. Because of the center, US becomes the leader in synthetic biology field. So, I mean, it's my tremendous honor again to have Professor Keasling. And with that, Professor Keasling, the virtual podium is all yours. And thank you so much for your time and your pioneering work. Always inspire us, and looking forward to your short sort of introductory speech for all of us. Thank you so much.
Thank you, Tae-Suk. That was a very nice introduction. So I was told to be inspiring in the 5 minutes I have today. And so I thought I'd give you a few pieces of advice that have guided my path as I look back on my career. The first piece of advice is to find your passion and try to make it your life's work. I was a teenager at the start of the genetic engineering revolution, and I remember reading in fascination about the idea of manipulating biology to create life-saving medications. In 1984, I took my first genetics course, and it reinforced my fascination with genetic engineering and led me down a path that I'm still on today. Engineering microbes to produce therapies to fight disease and to produce chemicals that are better for the environment than the ones that are now produced from petroleum. People often ask me what my hobby is, and somewhat embarrassingly, I always answer my job or my career. I know this might sound lame to you, but it's really true. It's a very special privilege that I get up every morning and can do my hobby for work. I didn't choose it because it was easy or would make me lots of money. I chose it because it fascinated me, because it is difficult and challenges me, and because I just might be able to move the needle on making the planet a better place for my children and their children. I know I've been extremely lucky. I found my passion early. I had a supportive family, and I can earn a living doing my passion. Not everyone is that fortunate, but everyone can find a passion and pour their spare time into it, even if it's not your work. Don't choose something because it's easy. Eventually, you'll get bored. Choose something that is difficult and may take years to master because it will challenge you every day. Don't choose something because it makes you lots of money. Choose something that makes you happy and you will never be poor. Don't choose something just because it makes your parents proud or impresses your friends. Choose something that makes you proud. Choose something that makes you want to jump into it when you wake up in the morning and keeps you up all hours of the night. Choose something that you will talk about to your grandchildren. My second piece of advice is to inspire others to pursue their passion. I think we have a lot of people in the audience from academics. And it's particularly important for academics. It's not like I came upon my passion all by myself. I was inspired by thoughtful teachers, professors, and mentors. In high school, 2 teachers saw my interest in math and science and inspired me to do my best in those subjects. In college, a few excellent professors inspired me to explore fields that were outside of what I knew and to get involved in research. From these stories about my own life, hopefully you will see a little inspiration can change a life's course. I ask all of you to try to be a positive inspiration to someone else and help them find their passion. You can do it as a parent, as a teacher, and in any career you choose, but particularly in academics. If you can inspire just one person to be the best person they can be, or to see a career path that they did not know, or to be a force for good, it will be a positive force multiplier in the world. And who knows what will come of it. Some people might become artists who make other people smile. Some people might become effective administrators who manage great organizations, and others might become scientists or engineers who build things to make people's lives better. Third, take big risks and don't be afraid of failing. Hardly anything of value is ever gotten without taking big risks. I have failed at far more things than I have succeeded, and that is the case for most of the successful people I know. Abraham Lincoln was one of the great failures of our time, or of his time, but he kept trying until he won the presidency. Chances are, if you have not failed, you have not challenged yourself enough and are not living up to your full potential. We tend to learn more from failures than successes. So if you fail early, you will learn from those failures and have successes later. Take risks while you are young and have less to lose. It gets harder and harder to take risks as you get older and become set in your ways. Don't be afraid to fail. If you do, you will learn and you will have successes later. And my final piece of advice is to value people. Everything I've accomplished in my life was a collaboration with wonderful people, family, mentors, colleagues, and students. People will always be your greatest resource. They will help you achieve your passions. They will inspire you and be inspired by you. They will help you de-risk the risky things you choose to do. Treat them as you would want to be treated, share credit with them, try to emulate the best mentors you have known, and help them to grow as you've grown. So with that, I will turn it back over to Tae-suk.
Oh my God. So fantastic talk as always. And you are always encouraging and inspiring us. And I am super honored to have you as my academic grandpa. And I'm lucky to be a SynBERC kid. Who had training by the center support and your guidance. So thank you so much for inspiring all of us. And I'm looking forward to your continued leadership in this field. And then, we all follow your footsteps and to make the world better. Thank you so much. Thank you. Okay, so now the main speaker of today with the longer introduction. Andrew Jones is an assistant professor at Miami University, Oxford, Ohio, not Florida. Prior to joining Miami, he spent 1 year as a visiting assistant professor of chemistry at Hamilton College. He completed his PhD at Rensselaer Polytechnic Institute. Dr. Jones joined Miami in the fall of 2017. His research focused on genetically engineering microbes for high-value chemical production using traditional and high-throughput molecular biology and biochemistry techniques. His lab takes a fine-tuned approach toward pathway optimization in bacteria for more efficient chemical production. His research has been highlighted on National Public Radio, Chemical and Engineering News, and Scientific American, to name a few. And additionally, he has been selected for multiple awards, including AICHE's 35 under 35, Bioengineering Miami University's Junior Faculty Scholar Award, and Miami's Outstanding Professor Award. He has published over 25 peer-reviewed publications in top journals and have been cited over more than 2,000 times since 2014. So Dr. Jones, please take it away. It's all yours now. And thank you so much for joining us.
Yeah, thank you for the introduction. I'll go ahead and share my screen. All right, does that look good, Tae-Suk?
Yes, wonderful.
Oh, fantastic. Thank you for the introduction. And Jay, thank you for the inspiring words. Following your passion, certainly something that I do. And I think that's something that guided me to go into academia. And I think as a short story, I think the first paper I ever read when I was trying to figure out what field I wanted to study in graduate school was actually a review written by kind of your lab. So I think that maybe you have some part in getting me into this idea of metabolic engineering, synthetic biology, and some of those early kind of studies that you did to kind of show some of the potential of this field, I think really have impacted a whole generation of scientists. So I guess to start out, a disclosure, I am a paid consultant at SynBYSS, and that SynBio has licensed IP and supported research in my lab that's contributed to the work presented in this presentation. Just want to say that up front. So I am a little biased, but I think I'm biased for good reasons. Either way, so I'll start out talking a little bit about Miami University. It's a little bit different than the R1s that maybe many people are familiar with. We have a moderately sized department, about 350 undergraduates, a small master's program, but notably no PhD program in engineering here at Miami. We pride ourselves in being one of the best undergraduate teaching universities in the country. And we've been around since the early 1800s. So we actually were a university before Florida was even a state. So we are the original Miami. We're named after the Miami Indian tribe that inhabited this area. Leading into kind of the talk and the topic I want to talk about, I want to start by introducing mental health. I want to talk a little bit on mental health and really highlight how big of a problem mental health is growing to be. If we look worldwide, about 1 in 8 people have a diagnosable mental health condition that they, but if we look more locally, right, that number grows to about 1 in 4. I don't know if people can see things. Grows to about 1 in 4 in the US, right? So this is a really big problem. This is something that impacts everyone's family, everyone's friends, everyone's colleagues, coworkers, classmates. So it's something that really needs to be kind of addressed. If we look at the life expectancy for those that struggle with mental conditions versus those who don't, we see almost a decade difference in mental health in their lifespan through a comparison of those two conditions, right? And that's a big number, right? That's a decade less life that you have. But that's also pretty equivalent to having a smoking addiction, right? So this is a really big issue in that context. And everybody understands that smoking is bad and smoking will shorten your lifespan, but that connection has not quite been made with mental health yet, at least as broadly. And so this is a very expensive problem, right? In the US, we spend about $190 billion a year is the kind of total cost of mental disorders, right? That's a pretty inclusive term that includes healthcare as well as kind of lost opportunity through kind of missing inability to kind of be at work and those types of things. And to put that into perspective, that's the GDP of Greece, right? So a major country in the world, right? The US spends that much money or has a loss of that much money every year. And despite spending this kind of in like a value of money that I can't even comprehend, we still have about 24% of those who are getting treatment for mental disorders kind of having unmet needs still, right? The treatments that are available are not really hitting the mark, are not working for what we need, right? So this kind of highlights that we need new mechanisms of action. We need new directions that we can go to help treat some of these conditions that are not well treated with current treatment strategies. If we look at some of the current treatments, these are typically serotonin selective reuptake inhibitors, but they have a lot of negative side effects, right? Many of those that people in the audience are familiar with, as I'm sure people in this audience have struggled with mental health care issues in their life or with their families' lives, right? These have a really slow onset to be able to determine their effect, right? Which means you might have to take a drug for weeks to months to be able to determine if that is going to work for you, right? And then you have to kind of wean yourself off on it before you come into a new treatment strategy. The current strategies have a pretty high treatment resistance rate, as indicated by that 24% stat presented earlier. There are cases of increased suicidality, especially in kind of adolescent patients that are struggling with this, right? And that's particularly meaningful because someone who struggles early in life, right, that is something that they carry with them for their entire lifetime, right? And also you have a need for a consistent daily dose of these, let's say, antidepressants, for one example. And the problem is that many of these mental health disorders are actually, the symptoms of that cause you to not be able to remember to take consistent daily doses of these drugs, which is where they get their best benefit, right? But kind of late in the 20-teens, there was this kind of renaissance of psychedelics, and people started to realize that psychedelics might have some potential to treat many mental illnesses, right? They've been studied clinically for depression, anxiety, post-traumatic stress disorder, even addiction. In 2018 and 2019, the FDA gave a breakthrough designation to 2 different psilocybin trials, saying that we're going to fast track these drugs because they are showing so much potential for an unmet need in clinical healthcare, right? So this is pretty exciting stuff, right? And this is right around the same time that I started at Miami, when I started working on trying to find a niche that would be kind of my lab's work. So I really like this plot. I show it in most of my presentations, right? And it's kind of an idea of, many people have this preconceived notion that psychedelics are inherently dangerous. So if we look on the y-axis over here, we see what they're calling a dependence potential, right? You can think about this as how addictive are these compounds, right? If you take it once, how likely are you to want to take it again in a short period of time, right? On the x-axis, we see a ratio of active dose to lethal dose. You can think about that as a safety metric. Those drugs that end up on the right side are going to be things that are inherently less safe, and those on the left are going to be inherently more safe. I'd like to highlight a few things. The ones that are very addictive and not very safe are your classic players that you would expect: your heroin, your morphine, your cocaine. If you ask somebody what a dangerous drug was, these are things that they would come up with, right? A little bit removed from that, we see things like nicotine, right? Things that are accepted to know, we know that they kind of decrease life expectancy. We know they're addictive, right? Those are things that are accepted by kind of the public as such. A little further away from there, we see things like caffeine and alcohol, right? Things that many of you have probably consumed today, right? And so they're in this kind of middle range of this plot, indicating that they're moderately safe, moderately addictive. But also thought it was interesting that I couldn't really draw a circle between caffeine and alcohol without including roofies, just kind of a side note. But if we start to look at kind of your traditional psychedelics, we see those at kind of this far kind of bottom left corner, right? Particularly kind of your tryptamine and lysergic acid based psychedelics. They have really no addictive properties that have been kind of documented. They're also active doses are quite small compared to their kind of lethal doses, indicating that these really are safe drugs, right? Many of you may have heard from your parents or school teachers that if you take psychedelics when you're a kid, you'll have this flashback 30 years later when you're driving your family down the street or down the road in a car, and that'll cause you to wreck and have all types of issues. This has never happened. This is all just made up. By and large, psychedelics are considered to be one of the safer drugs, right? The side effects are quite low. And there's also, we have decades of recreational use with many of these drugs to be able to help look at long-term side effects that are not typically able to be validated with new kind of drug entities that go through kind of FDA approval processes. So hopefully now I've convinced you that maybe psychedelics are safe and maybe they have some potential for future mental health care. And my work is not specifically looking at developing the drug and running it through the clinical trials, but mine is working on developing processes to produce these compounds at quantities that will enable testing efficiently and sustainably. So to do that, I use bacteria. So I use E. coli and I take the pathway from the kind of native magic mushroom and put it into E. coli, and then I manipulate how those enzymes are expressed to enable kind of efficient production. So I introduce this pathway to the audience. So we start with feeding a 4-hydroxyindole. So that is a substrate that is very close. So the native substrate that would be produced by the bacteria would be the indole, missing this hydroxy group. That's condensed with serine through promiscuous activity of the native tryptophan synthase, right? So no engineering was done for this step in our work, resulting in a non-natural amino acid 4-hydroxytryptophan, right? From there, that fits nicely into the biosynthesis pathway, where we have a decarboxylase that turns in 4-hydroxytryptophan into 4-hydroxytryptamine, a kinase that phosphorylates at that 4-hydroxy position, and 2 sequential methylations that add those kind of N-methyl groups on to the tryptamine to form the dimethyl version, which is the psychoactive compound, or at least the prodrug for the psychoactive compound. When psilocybin's ingested, this is a very stable form of this compound. When it's ingested, there's alkaline phosphatase activity that cleaves the phosphate group, resulting in a compound called psilocin, which is kind of the active psychedelic. And maybe this isn't the right audience to be claiming the benefits of the biosynthetic approach, because I think we all maybe agree on this. But this is a DNA encoded autocatalytic process, right? It's a one-pot synthesis. These are things that the synthetic chemist will never be able to achieve for chemistry such as this. We have a really low synthesis cost. For example, to be able to chemically synthesize this compound because of the complicated phosphate chemistry, it can cost thousands of dollars per gram for this compound to be produced, or the process that I've developed costs tens of dollars per gram. So we have a very nice cost advantage versus the competing technology. We get pretty high substrate yield. What's published is around 50%. We've seen even higher with some of our iterations on this process as we go. And we seem to see more efficiency as we get through scale, as we add more and more control systems to help manage dissolved oxygen concentrations and substrate kind of an intermediate product buildup. We able to see really nice advances, and some of that I'll talk about today. And I think the most important part that we can all agree on is that this process is way cooler than synthetic organic chemistry or mushroom farming. At least, again, maybe this is some of my bias showing. So I want to start off with a little bit of proof of principle. This was work that was led by, at the time, 2 sophomore undergraduates in my lab. This was maybe circa 2018 or so. We took the pathway from the mushrooms, right? And we expressed them on the T7 with a strong T7 promoter. We used a pseudo-operon configuration, right? Which is just a promoter in front of every gene in the pathway, a terminator at the end to end that kind of transcription. And we ran this fermentation just to see what we could find. And after a few tweaks, we were able to see a added shoulder on the edge of a noise peak in our HPLC. At this time, we had no standards for psilocybin. We didn't really know what we were looking for. We were basing on, we bought the same column as another paper that had been published from a group in Germany. And we were trying to figure out if we had made this. We took our samples that we thought we may have had some success with to a mass spec. So it was an Orbitrap mass spec where we get high resolution kind of mass. And we actually found a mass peak that matched almost exactly to the expected mass peak in positive mode for the psilocybin. But again, it was really small peak at the time. But we were able to get that kind of MS2 data. And we saw the fragmentation pattern that matched exactly with what would have been predicted for psilocybin, indicating that like this is one of those days in the lab, right, that maybe only come about once every few years, right, where you can kind of step back and say, whoa, I've really accomplished something here, right? We've created the first bacteria on the planet that it can produce psilocybin. I like to think about this as the bacteria's best day. It's like it was their favorite day in the lab. So building off of that proof of principle, right, I want to walk you through kind of the case study for psilocybin is the case study of how my lab tackles many projects. We start with kind of thinking about genetic optimization, right? Focus primarily on the pathway. From there, I took a series of promoters that are mutant T7s. So they're still inducible, they're still T7 lag, but they have reduced strengths. So there's small point mutations in that promoter region. And I scrambled those promoters across each of our genes that we were working with. And we screened hundreds of different combinations, looking for some combination that seemed to work better for psilocybin production in this wild type VL21 bacteria that we're using as the host. And if you remember, right, back to the proof of principle, we were sitting at about 2 milligrams per liter, so somewhere down here for our best producing to date strain. Again, strong T7, but by reducing the strength of those promoters, we're able to achieve a near 30-fold improvement on our production, indicating maybe now we have identified some elite mutants, right? But there's still more optimization that we could perform, right? So once we finish genetic optimization, in many cases, we go through a lot of different types. We maybe don't just do promoter engineering. That's what we did in this case. But we might look at different configurations of an operon. We might look at changing terminators, ribosome binding sites. But promoter engineering is kind of my bread and butter. That's where I've found the most success in my career. From there, we went and looked at some process optimization, right? So that I'm showing here we changed the concentrations of different media components, right? Maybe the concentration of the substrate that begins our process. It's got a little bit of toxicity. So more is not always better, as metabolic engineering oftentimes figures out. And then we look at methionine and serine. Serine is that first condensation step with the 4-hydroxyindole catalyzed by the native TRPB. And methionine is a direct precursor to SAM, which is the activated methyl donor that can go, that adds those kind of methyl groups at the end of our biosynthesis pathway. So there's ways to kind of boost those pools if those were necessary. And through that, we were able to go from 60 up to about 140 milligrams per liter. And again, all of this at this point are in 48 well plates, right? So in a very small platform, we can screen lots of different variations of media conditions and promoter combinations. Okay. Once we had identified, got a lay of the land, we're looking at that production landscape. We have an idea of our best genetically elite strain, and then we also have an idea on our best general starting conditions for process optimization. We then went through and scaled up into bioreactors. But first, I want to show you from a metabolomics perspective what this looks like. Okay, so what I have here is our 4-hydroxyindole. That's our starting substrate that we start with, right? All the way to psilocybin. And so these are in order of the intermediate products, in order of their pathway that we're moving. So at stage 1, our original proof of concept, we saw a tiny amount of psilocybin showing up in our case, but a big buildup of that kind of first intermediate product, that non-natural 4-hydroxytryptophan. Okay. After our genetic optimization, we see a shift. We see a decrease in the buildup of that 4-hydroxytryptophan and a big push. We see that 30x improvement in our genetically elite strain. And then by coupling that with some process and media optimization, we're able to kind of push that flux even further to get kind of our stage 3 optimization, that combination of genetic and fermentation optimization. To see almost a complete shift of flux towards our final product, right? So a buildup of this. So now we have elite genetic strains and elite conditions to enable higher, tighter production. And again, we're still at about 140 milligrams per liter. Pretty impressive, right? For the first time this compound has ever been made in a bacteria. Certainly better than what had been produced previously. Previous to this, there was a study in Aspergillus that had produced it recombinantly. We had beaten that titer, right? But we still felt there was room to grow. So from there, we went to a benchtop bioreactor, right? So this is a 2-liter setup by Eppendorf. This enabled us to kind of a few key points, right? Enabled us to control DO and enable a fed batch feeding strategy. But most importantly, it enabled us to have slow and consistent feed of our 4-hydroxyindole, right? I remember I said that was a little toxic. Okay, that way, and by controlling the feed of that, we're able to minimize the buildup that 4-hydroxytryptophan, which also appears to be a little bit toxic in our system. And by keeping those intermediate concentrations low, we're able actually to get better growth and better conversion to our final product. And this is the point when we published in Metabolic Engineering in 2019, where we achieved just a little over 1 gram per liter of psilocybin. And this is also the point in my career, my life changed forever, right? So here's some data. So we had published this paper, and as soon as this paper hit the press, I started to get phone calls from a slew of different news organizations interested in kind of interviewing me and talking about some of the research that we've done. At this point, I hadn't even realized how impactful some of this work could be. And these are news organizations that I've always valued and things that I've always looked for to find kind of high quality news, Scientific American, NPR, et cetera. There was also a slew of news agencies that I never thought would cover research in my kind of area. I never expected to pick up the phone and someone from High Times to be calling me, or Snoop Dogg's Mary Jane publication. So those were something that kind of was maybe unexpected, but in hindsight, I guess makes sense. And then some people just got it wrong. I never talked to Paul Seaburn, but I think he misinterpreted the communication of my research. I certainly did not engineer a bacteria that poops magic mushrooms, although that does sound intriguing. So here's a point where I want to give a little advice to graduate students, right? And I think one of the most important parts of doing research is communicating that with people outside of your research area. I try to make a point of every paper that I publish. I try to make sure that that gets written in a way that could be read and understood by non-scientific audiences. I work with many people at these types of organizations to write articles that help distill down the work and highlight the impact that this work could have and how it could change the world. I urge you to look to your university kind of press offices to have them put highlights out on some of your most impactful papers, right? In several occasions, I've reached out to editors at CNE and the American Chemical Society publications, so publication I really enjoy reading. I've reached out to them to kind of tell them about some of the cool research that is coming out soon, to have them kind of highlight that. And I think that getting that experience and being able to communicate your research with those audiences is something that's incredibly important. So at that point, once things had died down a little bit, I started to kind of cruise the internet looking for what else was being discussed about this work. And I stumbled onto Reddit, and I find a variety of people looking to start a black market for some of my psilocybin strains. I have a few people starting to talk about how maybe it's the future to start home brewing your own drugs through using genetic engineering. I found manifestos telling me about the price of plasmids and how much you could make, and summarized as, plus in a week or two of running even a small reactor at 1 gram per liter, you'd be in an extreme surplus of product and money, considering a dose of pure psilocybin is 25 milligrams. Which I'm still waiting on the extreme surplus of product and money, but I think you get the idea. So this got me to thinking. I wanted to know, like, if my strain did get outside of my laboratory, if somebody were to reproduce my work, have I opened Pandora's box? Could it be that you could homebrew psilocybin in your basement or in your garage? So I started to look into that a little bit more, looked into some regulatory considerations. It turns out the production strains are not regulated by the DEA. In my communications with the DEA, they didn't really seem to care that I had a bacteria that had this elite ability to take non-regulated compounds and turn them into psilocybin, which I thought was kind of interesting. And so I decided to ask, can I homebrew psilocybin? From there, I tasked a group of young students and said, let's see if we can figure this out, right? So we took some kind of standard stir plates with some media bottles. We used an aquarium pump to supply air into our system. And we used a kind of residential grade sous vide that you would typically cook meat with to kind of maintain our temperature in our kind of water bath. And to my surprise, we still were able to achieve over 300 milligrams per liter of production in this kind of rudimentary kind of setup that costs a few $100s to set up, as opposed to the $25,000 bioreactor that we used kind of for some of the published work. And to make it even more interesting, right? When I say basic homebrew, right? That's kind of throwing all, there's no antibiotics in this media. There is no sterile technique taken. We're not using flames to sterilize anything, right? We're barely washing our hands before we get started, right? And then by just adding ampicillin to that, that's able to increase production to be non-significant with our standard process where we use kind of more rigorous sterile technique when producing our media and setting up our system. So I think this was particularly interesting. So we published a paper, not as a how-to guide to produce your own psilocybin, but really focused on the regulatory considerations and made some suggestions that we think would be proper to facilitate both science still being able to advance, but also to put controls on some of this recombinant technology that could be used for clandestine efforts. And to kind of cap it all off, it turns out that we can do all of this and produce all of these compounds, and it's still only, the operating costs for that still only cost about 2% of the equivalent value of kind of mushrooms that you could buy illicitly. So there's also maybe this supreme surplus of money and product was not too far off by the Redditor. But this system is also really ripe for traditional metabolic engineering, right? At this point, we've really only focused on pathway engineering and process optimization. And we haven't looked at our host strain to make it a better host for psilocybin production, right? We've highlighted a few of the intermediates that are important for the production of these compounds, particularly serine, right, as in that first kind of condensation reaction. We did a little bit more work. This is norbacistin. It's a non-regulated intermediate product that makes some of our life a little easier. And we found that the native BL21 can actually produce plenty of serine through its natural pathways, or maybe better said, is our pathway is a strong enough sink to enable to pull flux towards serine. So that turns out is not a necessary addition to our media. But when we looked at methionine with and without, right? So if we look at the kind of solid lines here, without methionine, we landed a few hundred milligrams per liter, but with methionine, we can get up to our gram per liter titers. So we see a big delta there. And what that indicates to us is that we're SAM limited, right? So that SAM is the methyl donor that the methyltransferase would use twice to produce psilocybin. So we started looking at metabolic engineering around that SAM biosynthesis pathway. Okay, I've got the pathway here. You can see our methylation step would be here, right? So our psilocybin would get produced out this way. But SAM is an incredibly regulated intermediate. There's been much work from many of the top labs in the country in the metabolic engineering space, looking at kind of SAM biosynthesis and how to make methyl transfers more efficient in bacteria as well as other organisms. But you can see that this system really is ripe for metabolic engineering, right? We can knock out regulation, right? We can knock out kind of using feedback resistant mutants. You can take out cysteine and methionine kind of down regulation. We can knock out global regulators that would kind of down regulate the whole pathway, indicating that freeing up kind of flux to flow towards our desired product. We can also think about overexpressions of enzymes in that regeneration pathway, both recombinant enzymes in the SAH, it's native to kind of Saccharomyces cerevisiae, as well as the endogenous enzymes. So that leads us to have kind of a lot of potential options to kind of further tailor our strain for enhanced production. And I can't show you any of the kind of data. We're still in the process of getting that ready for publication. But hopefully you see kind of the potential that in developing a new strain, and we can build off the work of others to kind of develop a system that's going to enable high SAM availability and then enable us to produce psilocybin at even higher titers or develop strains that are better suited for our pathway of interest. Okay. So now I want to leave the psilocybin space. I want to start to think about other targets, other places we can use this kind of platform that we've developed and this method for optimization. So I want to talk a little bit about mushrooms, right? And so the typical way that psilocybin has been consumed for decades, arguably longer, is through eating the kind of whole natural product. And the thing about natural products is that they're not the same as a monochemical drug that you would take from a pharmacy, right? They're full of other metabolites, and those metabolites typically have evolved in some fashion that many of them oftentimes interact with each other, right? And specifically, when we think about psilocybin, we have different methylated versions, right? Both pathway intermediates as well as kind of a quaternary amine version that commonly shows up in these mushrooms. And kind of our hypothesis is that these molecules are more than just intermediate products. They're more than just stepping stones to get to psilocybin, but that they also have some interesting bioactivity. And these are compounds that haven't really been studied at all because of the legal ramifications of working with psilocybin. It's kind of limited work towards other intermediates in those pathways as well. But the problem is we couldn't really study these compounds because there's no commercial availability, right? At least at the time when I started this work, there was, I think now there are a few companies that will sell you some very high priced versions of these compounds. And so this is pretty exciting. I just started a collaboration with a colleague in psychology, Matt McMurray, working to do some animal studies to better understand many aspects of psychedelics and the compounds that I'm making. So we set out to try to make all of these compounds, right? To kind of further testing and see the application of our pathway or our system to other chemicals. So some of the work of Lexi Adams, who's now out at Stanford, she worked on developing a neurobiosystem strain, right? So that's a free amine version of psilocybin. So it's 2 methyl groups less. And we chose to start with that one because it was the easiest, right? So all we have to do to make neurobiosystem as our end product is to remove our Psy-M gene or methyltransferase. And that will give us a kind of a 2-gene pathway, right? Or at least 2 recombinant genes to end in that kind of final product titer. So all we did was we removed that kind of one open reading frame, and we kept the pathway configuration identical to what we'd seen before, right? We expected to see pretty similar optimization processes. And in some ways, we found it to be sensitive to the same kind of products, right? The promoter engineering was still something that gave us large enhanced production. But interestingly, it was a different promoter configuration that resulted in that kind of best production. So we have our initial screen data here. We tested both operon and pseudo-operon configurations of these compounds, very similar to what we did in the psilocybin case. We still found some operon structures, right? That means just a promoter and terminator at the beginning and end, respectively, to work better, but we saw several pseudo-operon constructs that worked well. But if we look at when we sequenced these kind of the best plasmids to produce this compound, and it was pretty interesting to see what we found, right? We actually found, so if we look here, psilocybin's in blue, it was the H10 variant that worked the best for us in the psilocybin case. But H10 was pretty much one of the worst in the norbeacystin case. And we saw this kind of bimodal activity as we think about low strength promoters to high strength promoters, right? C4 is actually a pretty interesting promoter that we found. It has a pretty slow rate, at least when expressing M-cherry, has a pretty slow rate of M-cherry production, but ends at a higher expression level than T7. So that one is frequently one that works well in our metabolic pathways in my lab. So that difference in the genetic optimization told us that anytime we change anything, right, we need to go back to the start. We need to rescreen these libraries, right? And it really motivates the need for kind of high throughput screening approaches, right? And really downplays the value of kind of a priori design and trying to predict exactly what promoter strength would work well on this gene for some reason, right? We just don't know enough about these systems and how they perform to be able to get that, to think about that up front. So from there, we worked on all our downstream purification, and we're able to get kind of purified drug that we passed off to the McMurray lab, which is he's an assistant professor in psychology at Miami. And we looked at a few kind of animal readouts, right? And this isn't directly my field, but I think it's something that motivates this work and makes it pretty exciting pushing forward. And the first thing we looked at is the head twitch response, right? And this is a behavior by this rat that enables us to distinguish if the rat is having hallucinogenic activity, right? It's maybe not a direct measure, as many of these animal studies aren't, but it gives us an idea. So the idea is when you give a rat a known psychedelic, they're going to have this kind of head rotation. And I've got a video here that I'll show you what this looks like. 2 head twitch events in this video. One's coming up soon, right there, that little head twitch. And there's another one right there, right? And so those are pretty hard to pick out, but can be picked out by video monitoring, okay? But you can also see that we have a magnet affixed to this animal's head. And actually on the outside of this container, there's a wire coil that enables us to kind of digitally pick up on that movement and filter in a way that allows us to kind of have a higher throughput processing for these animals. So that's one thing. We look for hallucinogenic response for some of these compounds. We also then look at, so building into that data, here we've looked at norbeacystin and psilocybin separately, and then the combination of the two. So if you look at norbeacystin in red, you can see that as we increase the dose, we see no increase in kind of these head twitch events. This indicates that we are not seeing a hallucinogenic response. We would not expect that compound to be hallucinogenic in these rats. However, when we give psilocybin, we see this kind of dose-dependent increase in head twitch events, which is kind of expected and what we would come up with from what matches with past literature for psilocybin. However, something that's pretty interesting, something that hasn't been really tested before, is that when we do the combination of these, trying to mimic kind of a mushroom-like environment, we'll say, we can see this increase in a dose-dependent increase, right? But that increase is greater in magnitude than what you would see with psilocybin alone, right? It's also greater than the synergy if you were to add the impact, the non-impact from norbeacistin with psilocybin, right? So this tells us that there could be some interesting kind of interactions or interplays with these compounds, but we don't really know that mechanism yet, and we're still looking into that, and that's something that's an active area of research, kind of in the collaboration between the Jones Lab and McMurray Labs. We've also looked at a few other things, the sucrose preference test, right? So the idea, rodents, just like humans, like sweet solutions, right? So if you give them the option of a water bottle and a sugar water bottle, they're going to choose the sugar every time, let's say. And but when you put animals through a stress paradigm that induces a depression-like state, right? All of a sudden, they don't care which water they're using, right? They become, they don't have a preference for the sweet water any longer. They have less preference for the sweet water, right? And then typically with traditional antidepressants, if you were to give them that, they would then regain that ability to prefer the sweet tasting solutions again. And what you can see here is that fluoxetine, which is the active ingredient in Prozac, which is a classic antidepressant, actually did not perform well in this test, right? And that's something that's been previously published. Many of these tests kind of give mixed results. However, our psilocybin, norbeacistin, and the combination of the two all showed an increasing reversal of that kind of sucrose preference, which is pretty exciting, right? Particularly for the norbeacistin, because it didn't show any head twitch events, had limited hallucinogenic activity. Okay, McMurray Labs also looked at forced swim tests, right? Which is the idea that you put an animal in an inescapable chamber of water and they're treading water, right? And then you measure how long it takes them to effectively give up, right? Or how, when they just sit there and float instead of trying to actively escape. And again, depressed animals will kind of give up more quickly, right? The animals don't drown, you rescue them, but we look at how much time they kind of try to actively escape from that scenario, right? And what you see is that with just a vehicle, we see kind of a really high immobility duration, right? But we see that decreasing, right? For known antidepressants, Prozac, as well as both of our drugs and the combination of our two drugs, right? So this all taken together leads us to kind of say, like, maybe this idea of this, maybe an entourage, or there's some mechanism working here that could be particularly exciting for some of these drugs that we're working to develop. Also, so in the last few minutes of my talk, I want to take some time and talk about some of the most exciting kind of new unpublished work that's happening in my lab. And because of that, I've kind of masked a few of the details, but we're hoping to get some of these submitted this summer, and hopefully we'll be able to kind of share all the details at that time. So the first thing we're doing is trying to take this platform and make a lot of non-natural compounds. I've talked up to now, it's all been talk of natural, naturally occurring psilocybin and its intermediate products. But if we think about modifying this core indole, remember we use the 4-hydroxy to get to psilocybin. But if we put some halogens, let's say, out here on this compound, on the kind of indole ring, we might be able to make new non-natural compounds that may still have bioactivity, right? But might have different kind of pharmacokinetic data or dynamic data. So the way we look at this is we feed the indole derivative, right? We measure its conversion to tryptophan, right? So that's with the native tryptophan synthase, that TRPB subunit in our bacteria, right? We then look at cells that are expressing our decarboxylase to see how much of that tryptophan could then be converted to the tryptamine. And starting there, because we have a large library of these compounds, we focus with just a single promoter. We work with that strong T7 as a starting point. We then went into screening different T7 promoters to determine kind of the best configuration, right? We tried to find a promoter variant that would enable the most conversion of that tryptophan to the tryptamine by controlling the expression of Psi-D. So what that looks like is we have kind of a range of different promoters and vector combinations and all types of operand setups. And we screen kind of that standard system where if we started with T7, it looks like the H9 configuration would have been a better choice, right? And so that's what we consider to be our best. Okay. And this is going to be a lot of data, and I'm running out of time a little bit, but I want to highlight this just a little bit. So if we look at TRPB, we've screened, it looks like 43 different compounds at this stage. And you can see that some of them process through to the tryptophan very efficiently, right? So we're talking about yield. So it's tryptophan over the remaining indole plus tryptophan. And we used peak areas to determine these yields because we don't have standards for all of these different compounds that we're making. But some of them worked really well, especially the 7 position appears to be very flexible for the TRPB, where other positions maybe not so much. But then coupling that TRPB activity with our Psi-D, right? And again, this time we're presenting yields, but these yields are with tryptamine over tryptophan plus tryptamine, right? So we're trying to isolate just the Psi-D activity. So it's after TRPB makes the tryptophan, how much of that tryptophan is converted to tryptamine, right? And some of these are pretty efficient. So Psi-D seems to be pretty open on the 4 position for a few of our different indoles or substitutions. But then many of them are much lower, right? We see lots of zeros, lots of 1s, 2s, 5s, 8s. But this is where we had started to, and that's what motivated us to look at that optimization process for the Psi-D. Because when we were able to screen that kind of library of 10 or so different configurations, we're able to find conditions that would get near complete conversion for almost every substrate that had worked originally, right? With a few notable exceptions. So we have quite a few kind of setups going through to that kind of tryptamine stage, right? Which gets particularly exciting because now we can start to think about how do we take those tryptamines and get them to the kind of psilocybin-like or those dimethyl versions. Before I go too far, we have started looking at kind of enabling the de novo production of this compound in our bacteria. We see by taking the PSIH from the mushrooms, we're able to, and the reductase partner, because it's a P450, we're able to see some activity of these compounds, and we're still in the process of optimizing some of this a little bit more completely and looking at kind of a wider range of different variables. But through building 12 different configurations, and that's varying all the different kind of N-term and C-term elements that you would have in a traditional operand structure, we're able to find one particular configuration that made about 30 milligrams per liter of 4-hydroxytryptamine. And that would be kind of de novo. So it's pretty exciting because indole and serine are kind of can naturally produce tryptophan with bacteria. But the most exciting part of this work is that we can now couple this kind of natural hydroxylase activity with some of the non-natural versions, right? So we could feed to 7-methyl indole, we could add that 4-hydroxy with the P450, and we see substrate flexibility there, right? So in the top figure here, we're showing just kind of de novo psilocybin production. We're in our control, you see no peak here, and then that's our psilocybin peak. Again, not a ton of production, about 30 milligrams per liter, indicating that P450 is the limiting case. But coupling that in a co-culture, we're able to feed some of our derivatized, in this case, I'm showing the 7-methyl, and we're able to make 7-methyl psilocybin. And in fact, we've been able to do this for over 13 different derivatives at this point. So now we have this kind of ability to use our platform to produce all of these different non-natural compounds that might have therapeutic benefit and are actively being explored in that space. We haven't stopped just at psilocybin. I have one of my grad students, Lucas, his master's thesis is all about DMT biosynthesis and enabling DMT biosynthesis. And we have been successful there. He actually defends next week, and we'll get this paper submitted shortly thereafter. But we have identified a methyltransferase, right? It's not the same one as psilocybin. That psilocybin methyltransferase is very specific to that 4-phospho group being there. But we're able to identify a methyltransferase that can enable tryptamine by methylation to result in a whole variety of these different compounds. The dimethyl version would be the DMT, or the kind of scheduled active compound that's naturally found in the ayahuasca, the kind of native South American drink that is used for kind of spiritual and religious purposes. So that's something that's pretty exciting to share with everybody soon in publication. And again, there's a few details that are kind of masked here. That's just total methylated tryptamines and those types of things. And we have some kind of data that kind of exceeds this, but this is what has been protected already from an intellectual property perspective. So looking forward, or maybe looking back first, then forward, in May of 2020, a lot of this work was licensed to SynBYSS, which at the time was a startup kind of venture capital based biotech company. About a year later, they actually went public in Canada. So at IPO on the Toronto Venture Exchange. And they're actively supporting research in my lab and working towards developing kind of a clinical strategy to get some of these compounds in humans in the near term. And from my perspective, I'm looking at kind of leveraging this platform to make as many new molecules as we can, hoping that we find one that's going to help benefit people that are struggling with mental illness, that especially those that are treatment resistant for current strategies. With that, I must thank my team, right? I'm a firm believer that in academia, the most important research product that you have are the people that you train. And these people are all stars and certainly do the bulk of the work in the lab. So I certainly have some of the best in the business, and I'm proud to send them off to go do big things and solve the big world problems once they finish with me. With that, I'm happy to answer any questions, and I appreciate everybody taking the time to listen.
Wonderful. So thank you so much. I mean, it's fantastic talk. So let me see whether we have question. If you have the question, you could raise your hand. But let me check first. Chat. Okay. Then Q&A. Okay, so I have question to start. So you show very interesting, also very delicate kind of topic, so the solution and promising thing. But could you kind of share some your perspective or your future direction in terms of this very interesting, but also probably a little bit sophisticated kind of, the target compound and then the production.
Yeah, so
you already we already mentioned some of that, but I always, in the future, what you should do, that remaining challenges and so on.
Yeah, so I think there's a wide variety of remaining challenges, right? So this technology is pretty competitive. I would argue it's the best in the world. But the biggest competitor from my perspective is synthetic organic chemistry, right? But the problem is they have that phosphate chemistry that they struggle to do efficiently and cost effectively. So to remain competitive, I'm always looking to enhance the production of our kind of core psilocybin biosynthesis strain, right? So that's something that we have lots of ongoing projects in my lab looking at different mechanisms to increase strain stability and lengthen productivity and enhance kind of activity and all types of intermediates and cofactor regeneration processes, like traditional metabolic engineering approaches to improve that. We are sitting in a good spot where we're well over 1 gram per liter production consistently in our best strains. And that makes it competitive. But if we could get that to 4 or 5 or 10 grams per liter, right, that's going to make the downstream purification easier, right? And that's something that we have accomplished in our lab at small scale to be able to provide purified drugs for animal studies. But it's something that at scale is a challenge. So it's something that we're actively looking at and looking to improve upon. So my lab is going that way. I find some of the downstream stuff to be a little bit boring and stale. And so I like the genetic engineering. That's where I focus most of the talks. But I also, in the same sense, right? It's like when you're trying to make a drug, right? You don't want to if you make just one drug, right? There's a chance it's going to fail. It's a chance that, you have to remember psilocybin has this, even if it does help with mental health, care. It has this large side effect of being psychedelic and having this like 6-hour voyage to another planet every time you take it, right? So that's a big side effect that the other technology does not have. So we're actively looking for new compounds, right, that hopefully can kind of detangle or detach the idea of a psychedelic experience with the mental health treatment, right? And maybe we've stumbled onto something here with the norbeacistin. But it's still yet to be determined, right? Mechanisms of action are not really known, especially for the mental health treatment side of things. The psychedelic side of things is pretty well known, but we're still trying to figure these things out. So I think that collaborations, right? That's why I really value a collaboration with the McMurray lab. It's like I can work on producing new compounds, right? And he thinks about ways to evaluate them and pick winners and guide which directions that I focus my research. So it's really a collaborative effort, and it's a large, it's not something that one person can do or one set of expertise. You have to have these kind of diverse teams that are going to tackle big problems.
Sure. I will check one more time, Q&A and chat. Okay, so thank you so much for your talk and answer to my question. And this is already 1 a.m. actually 1:10 a.m. right now my time, so I probably need to close. So thank all for joining and staying today, and we will meet again next week on June 30th, Thursday, the same time, the same Zoom link. But I will be joining, as I mentioned, from Cancun, Mexico. Why not? After my 17th talk, we'll have Dr. David Rampulla, NIH director, and Professor Xiaojing Gao at Stanford University, where I started this crazy 10-week seminar tour. As usual, the follow-up informal chat will occur without recording. So please stay here if you are interested in chatting with today's speaker, and I will promote you to panelists who can speak and show your handsome and pretty faces. So thanks all of you, and I've stopped recording. Let me stop.